Hello students, last lecture we have seen the problems on composite wall and with the overall heat transfer coefficient. Now in this lecture we will see heat conduction through a hollow cylinder. So we know the generalized heat conduction equation in Cartesian coordinate. We know this generalized heat conduction equation in Cartesian coordinate, dou square T upon dou x square plus dou square T upon dou y square plus dou square T upon dou z square plus Qg by K 1 upon alpha dou T by dou tau. By using this equation we have derived the derivation for the plane wall and as well as the for composite wall by using this equation. Similarly, there is a equation for cylinder. So this is a final equation for cylinder. There is general heat conduction equation in cylindrical coordinate, and this equation is for a sphere. Now, by using the cylinder equation or this equation, we will derive the heat conduction through hollow cylinder and then heat conduction through the composite cylinder. Okay. So let's see here in this figure where this is a composite this is a hollow cylinder where this is R1, so that is a radius of inner cylinder. Okay, now R2, that is a outer radius, so this is a R2 is a outer radius. Now here T1 is a inside temperature, T1 that is inside temperature, T2 is a outside temperature. Now here we have selected the element area. So here you can see this is the element area which is having thickness dt, which is having a thickness dr, and temperature difference is a dt. Now heat is transferred from this T1, so inner temperature is greater than outer temperature, so heat is transferred from T1 to T2. Now here heat flows radially outwards, so we will consider T1 is greater than T2, and this cylinder having a length of L. Now consider this is a cylinder, hollow cylinder, which is made of a same material throughout. So we are considering this is a cylinder made of a same material throughout and with a constant thermal conductivity. Now we know the general heat conduction equation in cylindrical coordinate is, so I will write once again here equation. So that is equation is dou square T, okay, dou square T upon dou R square plus dou 1 upon R plus 1 upon plus 1 upon R plus 1 upon R dou T by dou R plus 1 upon R square dou square T upon dou phi square plus dou square T upon dou Z square plus Qg by K is equal to 1 upon alpha dou T by dou tau. So this is the equation for general heat conduction equation in cylindrical coordinate. So here in the radial direction, in phi direction and in Z direction. So three directions are used here. Okay. Now for solving this equation, we will consider there is no internal heat generation. No internal heat generation means consider Qg is equal to 0. So this term is becoming now 0. When there is a steady state condition, means dou T by dou tau is equal to 0. When there is a steady state, means temperature does not depend upon time, that time this term is now becoming 0, and there is only one direction heat flow. So in the heat flow in the radial direction, so we will not consider this phi direction and this Z direction. So we will consider only R direction. So this equation becomes, so this equation become dou square T upon dou R square plus 1 upon R dou T by dou R plus, plus is not there because it is considered as 0, so is equal to 0. So our equation becomes dou square T upon dou R square plus 1 upon R dou T by dou R is equal to 0. So this is a equation. Now this equation you can write this equation in the form of, or we can write this equation as 1 upon R d by dr R dt by dr. So how this equation comes? We can write instead of this equation 1 upon R d by dr R dt by dr. So how this come? So we know that d by dx of u into v. So we know that it is a u into dv by dx plus v into du by dx. So similarly we will consider this d by dr R dt by dr here. So this is d by dr R dt by dr is equal to, so here we will consider R is nothing but u and dt by dr is nothing but the v. If you solve this, so I will solve here. After solving this, we will get that u as it is into d square t upon dr square plus v as it is means dt by dr as it is, and it is with respect to r, so with r it is becoming 1. Okay, so u is nothing but here, so u is nothing but r, we can take down, that is a r d square t upon dr square. If we divide this total equation by r, so our equation becomes, so this become dou square t upon dou r square plus 1 upon r t by dou r or dt by dr. So this is the same equation like this. Okay, this equation and this equation same. So this is a expanded form of this equation. Okay, so both equations are same. Now again we will solve further this equation. So this part you have to write in the examination, or you, if you not written, it's okay. Okay, so this is a simplification. Okay, 1 upon r d by dr, r dt by dr is equal to 0. Now when these are going towards this side, that becomes 0. So equation remains d by dr r dt by dr is equal to 0. Now as similar to the wall equation, we have to integrate this equation twice. So we have to integrate equation twice. So first integration you will get, first integration is r dt by dr is equal to c1. Okay, after first integration. Now when these are going toward the other side, it become dt by dr is equal to c1 upon r. So dt by dr is equal to c1 upon r. So we will require this equation. So I am giving a equation number 1. Okay. Now second integration. So here it will become t is equal to c1, 1 upon r, that is nothing but the ln r. So 1 upon r is nothing but ln r. So here we will take C1 into ln R plus another constant C2. So this is a temperature distribution equation. Now I will give equation number 2 here. Temperature distribution equation where C1 and C2 are the constants and value of constants calculated from the boundary condition. So C1 and C2 are constant. Now what is the boundary condition? So boundary condition from the figure. So boundary condition from the figure. So first boundary condition, when r is equal to r1. So here in the figure we have considered this is a element area. So this is the element area which is having a radius r1 r. Now when this r is inside radius, so when r is equal to r1, that time temperature is inside temperature, and when this r is equal to outside radius, that means r2, that is temperature is equal to outside temperature T2. So these are the boundary conditions. So when r is equal to r1, that time temperature is equal to inside temperature, and second boundary condition, when r is equal to r2, that time temperature is equal to T2, T is equal to T2. So these are the two boundary conditions. We will put the equation in the equation, that is temperature distribution equation. So just I will put here value in this equation. So instead of T I am putting T1 is equal to C1, and instead of R I am putting R1. So C1 ln R plus C2. So I will give here equation number 3. Now putting the second boundary condition in this equation, instead of T I am putting T2 is equal to C1 ln R2 plus C2. So I will give here equation number 4. So we cannot get the value of C1 and C2 directly. So here we will again rearrange the equations C1 and equation number 3 and equation number 4. So we will do equation 2 minus equation number 3. So subtracting equation 3 from equation 2. So equation 2 minus equation number 3. So I will write here left hand side here. So here this become T1 minus T2 for left hand side, and in the right hand side that is C1 ln R1 plus C2 minus, now I am putting in the bracket, so here C1 ln R2 plus C2. Okay, when we remove this bracket or taking outside the bracket, so this equation becomes C1 ln R1 plus C2 minus C1 ln R2 minus C2. Now here plus C2 and minus C2 cancel, and common part is a C1 in these two equations. So I am taking common C1. Inside the bracket it is ln R1 minus ln R2. So ln R1 is nothing but the log base E. Okay, ln R1 minus R2, or we can write this equation C1 in ln R1 by R2. So that is equal to T1 minus T2. But here we require the value of C1. So I am again rearranging this equation. So we will get the value of C1. C1 is equal to T1 minus T2 divided by ln R1 by R2. So here we will get the value of C1. Now, once we got the value of C1, we can put this in the equation number 3 or equation number 4. So, I am putting in the equation number 3, value of a C1 in equation number 3. So, I will just first write down the equation number 3. So, that equation is T is equal to C1 ln R1 plus C2. So, that is equation number 3. Now, I am putting the value of C1 here. So, this equation becomes T is equal to, so instead of C1, I am putting T1 minus T2 divided by ln R1 by R2, and into multiplication is ln R1 plus C2. So, taking this term toward the other side, we will get the value of C2, or I will write here value of C2 here. So, when taking this term toward the other side, so C2 becomes T minus T1 minus T2 upon ln R1 by R2 into ln R1. So, this is a value of a C2. So, after solving these two equations, we got the value of C1 and C2. Now, we will put these two values again in a equation number 2. So, that is a temperature distribution equation where C1 and C2 are the constants. So, we got the value of C1 and C2 again putting in the temperature distribution equation. So, I will write once again the temperature distribution equation. So, that was T is equal to C1 ln R plus C2. So, that was the temperature distribution equation. Now, we will put the value here. So, T is equal to value of C1 is T1 minus T2 upon ln R1 by R2. So, T1 minus T2 upon ln R1 by R2 into here ln R, I will keep as it is ln R, plus value of C2 is here. So, that is T minus T1 minus T2. So, here this is not T, so here it is a T1, actually here it is a T1. So, T1, so this is a T1. Okay, so T1 minus T1 plus T2 divided by ln R1 by R2 into ln R1. So, here we got the temperature distribution equation. T is equal to, now I am taking this T1 toward the other side. So, taking this T1 other side, so it has become negative. So, this equation becomes now T minus T1. So, this equation becomes, when taking T toward other side, so this becomes T minus T1 is equal to, and if you check in the problem, the common part is T1 minus T2 upon ln R1 by R2. T1 minus T2 upon ln R1 by R2. So, I am taking that part as a common. So, T1 minus T2 upon ln R1 by R2, and inside the bracket now remaining ln R minus ln R1. So, again we can simplify this in the form of T1 minus T2 upon ln R1 by R2, and here ln R by R1, because it is ln R minus ln R1. So, here this equation is T minus T1 is equal to, or you can write this equation, in the form here. So, I am writing T minus T1, taking this term to our other side. So, here it becomes T1 minus T2 is equal to, now other side is ln R by R1 divided by ln R1 by R2. So, this is a temperature distribution equation. So, by using this equation, we can find out the temperature at any location. Suppose that inside radius is given 10 centimeter, outside radius is given 20 centimeter, inside temperature is given 100, outside temperature is given as a 50, and if it is asked, find out the temperature at 15 centimeter. Okay, if the problem is asked when find out the temperature at 15 centimeter, so we can put the value. So, here T is a temperature at a 15 centimeter. We know T100, T2 50. Now, when R is where we want the temperature, so 15 centimeter. So, R now become 15. R1, that is the inner radius is given. R2, that is outer radius is given. So, by using this formula, you can solve the equation and find out the temperature at any location. So, this is a temperature distribution equation. Now, we will find out the heat flow rate. So, heat flow rate, that is from the Fourier's law. So, Fourier's law is equal to Q is equal to minus Ka dt by dx, that is for wall, but here dt by dr. So, here this equation is Q is equal to minus Ka dt by dr. Now we know that equation number 1, from equation number 1, so we know equation number 1 was, equation number 1 is here, dt by dr is equal to c1 upon r. We can solve this by 2 or 3 methods, so I will solve by 2 methods. So equation number 1, we know that dt by dr is equal to c1 upon r. Now here, what is the value of c1? So we know the value of a c1 is t1 minus t2 divided by ln r1 by r2. So this is the value of c1. Okay, so I will put here a value of c1. So value of c1 is t1 minus t2 divided by ln r1 by r2. So into 1 by r, we will keep here as it is. Okay, now this is the value of dt by dr. Now I am putting in the Fourier's law equation. So in the Fourier's law, now here q is equal to minus k into area. So into area is 2 pi r l. So that is the area, and dt by dr I will put here t1 minus t2 divided by ln r1 by r2 into 1 upon r. So now this r and this r gets cancelled. Now you can write equation q is equal to, so this is minus k 2 pi l t1 minus t2 divided by ln r1 by r2. So this is the equation. So you can give this minus sign inside the bracket. Okay, so here if you give the sign here, so it become t2 minus t1, but t1 is greater than t2, so I will give the minus sign to the denominator, and this equation becomes, so q is equal to, I will write here 2 pi kl, negative sign giving here, so t1 minus t2, and here instead of ln r1 by r2 it will become ln r2 by r1. So this is the final equation for the heat conduction through the hollow cylinder. Or you can solve this by other method also. So I will solve here this by the other method. We know that q is equal to minus ka dt by dr. Okay, so where we know the area is 2 pi r l, so that is a surface area. So I am putting a area here. So q is equal to minus k into 2 pi r l dt by dr. Now taking r term one side and dt term on other side, so I am taking dr here, so this become q into dr, and taking r dividing here is equal to minus k 2 pi l and dt. Now this is integrating from 1 to 2, initial to final condition 1 to 2. So what is initial condition? So there is radius 1 inside radius to the outside radius, and inside temperature to the outside temperature. If you solve, you will get the equation. So q into ln r2 by r1 is equal to minus k 2 pi l t2 minus t1. So once you give this negative sign inside the bracket, so this become k 2 pi l t1 minus t2, and other side q ln r2 by r1. Again, if you simplify this equation in the form of q, you will get this 2 pi kl t1 minus t2 divided by this ln r2 by r1. So this is the final answer, okay, by this method also. So this is heat conduction through the hollow cylinder. You get the equation for hollow cylinder. So in the next lecture, we will see heat conduction through the composite cylinder and the problems on a composite cylinder. Thank you.